Hello, my name's Martin Chapman, and today I want to talk about a piece of work done by King's College London and Northwestern entitled Phenoflow, a microservice architecture for portable, workflow-based phenotype definitions. Specifically, I want to talk about the concept of portability. That is the effort associated with realizing a computable phenotype from its definition. I want to talk about a model that we've introduced, a new definition model, and associated authoring architecture that's designed to improve portability. I have no disclosures. I want to start by just revisiting the difference between a phenotype definition and its computable form. As we know, a phenotype definition is an abstract outline of functionality, something like a flowchart like we see here on the left, that really contains the logic for a phenotype, and this is then used as the basis for realizing a computable phenotype, so something that can be actually executed, that realizes that logic in something like an SQL script, a piece of Python code, or a pipeline like we see here. There are some challenges associated with phenotype definitions, particularly in respect of portability. Two I've highlighted here. So the first is in terms of complexity. So we need our definitions to be accurate enough to make them reproducible so that they can be accurately re-implemented at different sites. But this does create complexity specifically in terms of structure and terminology. So in trying to make as accurate a definition as possible, you might end up with quite a complex structure and quite complex terminology. And like I say, this is important for accuracy, but does increase the effort of realizing a definition in a computable form. The second is a practical challenge in the sense that the typical phenotype definitions that we've seen, like the flowchart that we saw earlier, that says very little about how we actually realize a computable phenotype in practice, which again reduces portability by definition. To address this issue, in this work, we introduce what we call a workflow-based model. So this is a model that's segmented both horizontally and vertically. Vertically, the model is segmented into three layers: abstract, functional, and computational. And horizontally, it's segmented into a number of different steps. So at the abstract layer, which is akin to the regular phenotype definitions that we've seen, such as flowcharts, we segment the model into a number of different steps, with each step containing a piece of functionality from the phenotype definition. And then we have these two additional layers, functional and computational, which tell us more information, give us more low-level information about the actual implementation. So the first is specifying metadata associated with information passed between each of the steps in the abstract layer. And the final is computational, which starts to say some much more concrete things about the actual implementation itself, such as the environment in which it's likely to be executed. Here's a graphical overview of an individual step within our model, just to summarize what I've said. So, like I said, this is an individual step, so it'd be steps both before and after. And here we can see the three layers of the model: the abstract, functional, and computational. And we can see how then the implementation, which is marked here as implementation units, how those units can then be linked to that model and realized from it. So you get this nice connectivity between the model and any implementation. Then here we can see the actual realization of this model for an actual phenotype definition. This is a step of a COVID-19 phenotype. So we can see all those fields are populated. That definition's been completed there for the abstract, functional, and computational layers. And then from this, we've been able to realize these implementation units. And the key thing is the modularity here. So a single step of the abstract layer in our model can be realized in multiple ways, and that's something that we'll return to later on. So the second component of our work is this notion of our Phenoflow authoring architecture. So we don't actually expect researchers to manually construct their definitions under this model. To help with this, we provide an authoring architecture, which provides an authoring tool through which these definitions can be created. And the idea then is, if people use this architecture to author these definitions and add their implementations to the architecture, then these can be coupled together and downloaded as a realization of our model in what we call the common workflow language. So an actual computable form of the definition that can be executed. And the key thing here is that our architecture is realized as a set of microservices, so to ensure it's scalable and to ensure that it's robust, we split our architecture, we split this authoring architecture into a number of different services. The main one that the user will interact with that you'll see screenshots from is the web portal. This is also supported by other services such as a generator and a visualizer, which help with creating the workflows and visualizations of them, respectively. So what does the authoring tool look like? So here's an example of Phenoflow, which you can visit online, where you could actually build definitions according to this model. You can see here entering information for one of the individual steps. So you can do this authoring directly, or you can use an API, or indeed you can bulk import existing definitions. So once you've actually defined each of the steps in your model, you can then proceed with implementation. So you do so by then uploading an implementation for each of the steps. As we can see here, this is the realization of the COVID-19 phenotype that we saw before. And here someone is uploading a realization of their initial step, which is to read potential cases from disk, and they're uploading an implementation of this in Python. So once this, both authoring of the definition and actual realization has been completed, Phenoflow then will allow you to actually download this definition and the coupled implementation units and execute it in a local environment against a local data set. Something like OMOP, maybe something like FHIR or I2B2. Phenoflow provides connectors for each of these. So as a part of this work, it was very important for us to determine whether this model was suitable for capturing phenotype definitions, and also to determine its impact on portability. So to first investigate the suitability of the model, what we did was we took two phenotypes. The first one we took was a type 2 diabetes phenotype and its associated implementation. We selected a cohort, so this was around 26,000 patients from Northwestern. We then took the definition and we reauthored it according to Phenoflow. So before it was, I believe, the phenotype that we saw earlier, the flowchart form. So we restructured it according to the multi-layer, multi-step model. And we then, using Phenoflow, provided some implementation units for that structure and were able to generate the CWL implementation accordingly. What we could then do is take the original form of the original computable phenotype derived from the original structure of the definition and execute that along with the new computable phenotype derived from the new model and confirm that the results were the same using a particular gold standard. And indeed, we were able to confirm that, which shows that indeed our model still effectively captures the logic associated with that definition. To make sure this was as holistic as possible, this evaluation, we repeated this for COVID-19 phenotype, which we took from the UK, from Guy's and St. Thomas's. And what we did was exactly the same process. We took the original definition, we've got a computable form for it. We then restructured it according to the new model, generated a CWL implementation from that, executed both against the same data set, which is about 1,500 patients from GSTT, and we confirmed that the same cases and controls were found by each, and they were indeed, again confirming the suitability of our model. It was also important for us to determine any impact on portability that our new model had, because that was the overall aim of this work. And to do this, we employed what we call the Knowledge Conversion, Clause Interpretation and Programming, or KIP, scoring system, which assigns a lower score to phenotypes that are considered more portable. And it does so across a number of different dimensions. So the first is knowledge, so the effort associated with interpreting the information within a definition in order to be able to implement it. Also, another dimension is clause interpretation, so the effort associated with understanding the structure of a definition in order to be able to implement it. And the final dimension is quite a practical one in terms of programming, so the actual programmatic complexity of implementing a definition from the information that's provided, actually realizing it in a computable form. So what KIP allowed us to do was to actually compare the portability of our two phenotypes, our code-based phenotype COVID-19 and our logic-based phenotype type 2 diabetes. It allowed us to compare the portability of our definitions both unstructured, so before the arrival of the Phenoflow model, and then when structured under the Phenoflow model. And the results that we got are presented here. So in terms of knowledge, we saw little impact in terms of the code-based phenotype. So in the end, they are essentially just code lists, so the information is there and it's quite intelligible. However, we did see some impact in terms of the logic-based phenotypes, which tend to have greater reliance on more use of terminology. So having the multidimensional descriptions within Phenoflow, which adds information such as the type of logic that's being used or longer, more human-readable descriptions, having that present within the definition itself really helped address these issues with knowledge interpretation. In terms of the second dimension, in terms of clause interpretation, So we saw quite a significant impact in terms of code-based phenotypes. So without our structure before the arrival of the Phenoflow model, there's very little communicated in just a list of codes about things like the order in which those codes should be applied. And when the Phenoflow model comes along, it makes those things concrete. So that provides us with portability gains in terms of clause interpretation. We saw less improvements in terms of logic-based phenotypes. So again, the restructuring of under the Phenoflow model didn't have too much of an impact in terms of clause interpretation. But in terms of programming, so the actual practical task of realizing these phenotypes in code, we saw huge improvements. Again, because of all the information in the Phenoflow model that's able to be provided about practical things, practical ways in which these phenotypes are realized. So just to summarize, how have we addressed these definition challenges? Well, in terms to address structural issues and terminology issues that reduce portability, we've now added this clear step-by-step process to our model, this step-by-step structure. We've added these multidimensional descriptions as well, which also help with issues with terminology. So this allows us to retain accuracy, but also allow definitions to be portable. Second of all, in terms of this practical issue of realizing a phenotype from its definition, as we've seen through the Phenoflow model, we've been able to add information that guides implementation, such as information about execution environments and structure. Of course, beyond the model as well, Phenoflow itself, so the actual authoring library, does also help with portability. Specifically, we've seen that we can author a definition and add an associated implementation unit, but also future authors can add alternate implementation units. And what this provides is actually the ability to customize your downloads. So you can customize the type of implementation units that are combined in a kind of modular way when you go to download a phenotype. What this allows you to do is to build something or create something that you are comfortable editing. Future work will focus on a number of different areas based upon this initial idea. First of all, we're going to look at how we can leverage the multiple layers of the model to add more granular library search. Second of all, we're going to look at how, again, we can leverage the multi-layer model to look at relationships between phenotypes, so ideas of subphenotypes. And then quite practically, we're going to look at providing libraries of workflow modules. So for example, more variety of different types of connectors. So at the moment, we support I2B2 and OMOP, as well as CSV, so we want to add more connectors. And finally, we want to think about things, more subtle things like data conversion. So for example, how can we, behind the scenes, convert a CSV file to something like a database or an SQL format so that we can execute associated SQL scripts against it. Finally, I want to close by providing links to Phenoflow, which you're welcome to visit online. We have our actual site there, and also the repository, which is the microservice architecture that supports it. Thank you very much.